But some of you have already gotten to a point, so let's put some answers down. You should have seen a pattern between the period and the subtraction set, kind of, right? Everything except the very last one is going to kind of seem like you can form what we call a conjecture. So what did you see when you were writing down the periods between the subtraction set and the period? Can you predict what the period's going to be if I give you a subtraction set? Except for the last one. What did it look like? That's correct. It looked like you just add the two numbers together. For example, when the subtraction set was 1, 2, it looked like the period was 1 plus 2, 3. When the subtraction set was 2, 3, the period was 5, right? 2 plus 3. And I kind of knew that because when somebody said the period was 6, I said, no, it's not, because I know the period's 5. The next one also, 2, 4, ended up being what? 6. So that one was okay. Just you add it. The last one, the very last one, what'd you get as a period? 4. So it didn't fit that pattern. So here's how mathematics research works. You come up with conjectures based off of plain fooling around with it. It's a lot of fooling around. I hear people say, well, I'm creative. I'm not a math person. I beg to differ. I create all the time. I can tell you, looking at the different kinds of jobs that are out there, I know I wouldn't be qualified for some of those jobs. The ones that require me just to sit there and crunch, I wouldn't last too long in those jobs because I need to create. It's an art. I have a Bachelor of Arts in math, so it's an art. So this is kind of creative as you're going through, like, I wonder what's working, I wonder what's happening. So the first conjecture you should have been starting to formulate is, it looks like it's just the first thing plus the second thing, my period, right? But then you get to the last one, it's not true. So that tells you sometimes it's not the first thing plus the second thing. So the next thing a mathematician does is says, when is that? Can I separate that out and give you, if this, then this, if this, then this. Right? That's what we're looking for now. So if you haven't finished doing the computations, make sure you can, because we're going to be talking about this for a while. So if you want to do the write-ups separately and send them in on, when do we meet again? Next Tuesday? You can do that. I'm going to post a paper with all those solutions. I'd like you to take a chance, just try to read it. It's a real math paper, so it might be hard to read. It's a little dry when you read real math papers. You have to fill in the gaps. But it's the way I think I brought that to the table of combinatorial game theory. This is what I was doing before I was doing obesity research. Very, very different stuff. So I was taught in an area that focused on differential equations. How many of you took differential equations already or are taking it now? Some of you have taken it. So in differential equations, the way we talk about differential equations is we have y prime equals something, some function, right? And then you also have what we call an initial condition. This is how I was taught. Almost every one of the research talks we went to had something like this. So I took that training and background that I had for 5 years, and I looked at the game NIM the way I would look at a differential equation. So that paper that I'm going to post for you changes the NIM game to a recursion model that is a lot like differential equations. And that's really weird. And that's really, I think, that's creative. That's not rote computation. It's not the stereotype people have of a mathematician. But it's very typical. It's very typical. It's really odd that we teach calculus and it's so dry and it's methods oriented. But for our other side of our life, we're doing this kind of stuff. We're creating. And some of it is completely useless. And this never helped humanity, which is really interesting. So I'm going to post that for you, but on Tuesday, we're going to go through that way of thinking, because I think it's really neat, and it really knocks out some of the patterns that you're seeing. I'm able to prove those patterns. So I also think that's a mathematical way to think. You know, I have this idea, I think it's going to work, but then and I can be really married to that idea. I think it is the first one plus the second one, and then I find an example where it doesn't work. And I'm okay with that. And I'll try to reformulate my conjecture so it handles everything. But nothing's done until I have a proof. And I have to find an elegant way to prove that. And even if you take a job that's not in your specific area, once you've been polluted in that way of thinking, it's going to pollute you forever. You need a proof. You can't just say that. What's the definition of that? I don't understand what you mean. You have to explain that to me carefully. Soda makes you fat. Prove it to me. I need to see evidence for that. You know, so I bring that way of thinking to that other area of the obesity research that I do. So I think that math students will bring that also to the table, and that's something that you can write down on your applications. I think this way. And it brings a good amount of value to humanity. I think it does anyways.
Yeah.